you come up with these mathematical conclusions that are very robust and sound, and you can defend them. I mean, do you go back, Herman, to Hawking, and then does he say, sorry about saying rubbish, or I guess I was wrong about the rubbish?
To his credit, he has started changing at least his opinion, and he accepts a lot of these ideas. Einstein, for example, had a much harder time accepting quantum mechanics. I don't think he ever did. But Hawking, I think he realized at the time when he was putting this paradox forward, that by stating the contradiction that was in black hole physics, he realized that that was a way of making progress. And of course, he liked annoying his colleagues, which is sort of what he was doing by making this particular claim. But he put us to work. And then by the time that answers came forward, he had this bet with one of his colleagues that I think it was for a year-long subscription to Playboy. But in the end, the colleague decided to give him a nice book instead. Because the bet was settled, and then Hawking admitted that information was there, and so that's...
Well, the whole 2D, 3D thing, if you bring Playboy into it as a whole, that's... That's a whole other information space I don't even want to think about. As a much younger researcher, Raphael, what excites you about the holographic principle in terms of, and we're going to get into its controversy in a moment, in terms of what it begins to explain about other problems in physics?
I think what's exciting to me is that the only way that information could possibly not be lost when a black hole forms and then evaporates was for there to be a completely universal relation between the information content of a region and its surface area. In other words, there was a relation between surfaces in space-time, which are described by gravity theory. That's the realm of Einstein's general relativity. Surfaces surrounding certain regions. Those surfaces, their area specified how much information could be in the region that was enclosed by them. That turned out to be not quite the right way of stating it, but that was necessary if information was not going to be lost in black holes. In other words, it led to a statement about how much information there is in the world that was completely independent of what you were using to encode the information. It didn't matter whether you used letters on a page or atoms or strings or quarks, whatever your favorite physical ingredient was. It was a statement that was completely universal. If information was preserved, then we were learning something about fundamentally how much information there is in the world.
Well, even beyond that, we're learning that...
Let me just maybe say one thing, just to put that in a context. It's actually not very difficult to understand why this is so. Very roughly speaking, any place like this room can be converted by crashing some shells of matter into it, into a black hole that has the same surface area as this room. And we know how much information the black hole contains. So if information is not lost, that means that the information in this room, no matter what was in here, had to be less to start with than the information of the black hole, or at most equally much. And so it's completely universal. You don't have to know what we're made out of. You don't have to know what the fundamental bits and pieces of physics are. You already know how much information there is. And so it's a deep relation between the two things that we don't know how to put together, gravity and quantum mechanics. Quantum mechanics is about information, gravity is about geometry and surfaces.
But is it true, or is it a distortion to say, and again, for me, for a moment here, the idea of going to the black hole seems to confuse the issue, because the black hole is interesting because the way Hawking described it, information would be destroyed. That produces the controversy, which poses the question, all right, what is the relationship between information and all of the universe?
That's exactly right. That's exactly right. It was one of those questions where, people were just asking an incredibly interesting question, and as a consequence of resolving it, stumbled upon something that was much more general and didn't really just hold in this particular context of the black hole. In the end, you can throw the black hole away, and you're still left with...
Because I think most of the people in this room, the encounters with black holes are, monthly at best. So let's just say, because of the black hole thought experiment, controversy, argument with Hawking, we have stumbled upon or discovered or now see that a fundamental feature of the universe is that a two-dimensional space of information specifies everything in our universe.
Well,
something like that?
Initially, it
has
wasn't
to be that
clear how to apply this to the whole universe. Again, the context in which this was discovered was a very specific one, where you're far away, you throw some elephants into a small region, they form a black hole, and then it evaporates. And you want to ask the question, by looking at this Hawking radiation that came out, can I figure out if it was elephants or zebras that made the black hole? Now, that was resolved, I think, by now, pretty definitely. We can look at this, but our universe is nothing like that. Our universe is not like, like a black hole.
Right.
Our universe is not a place where you can go far away and study Hawking radiation coming out. And nevertheless, it turned out to be true that this was just the tip of an iceberg. There's a completely universal relation between information and area of surfaces. At first, it seems like that can't possibly be true. For example, if you don't take the viewpoint of the person who waits for the Hawking radiation to fizzle out of the black hole and then looks carefully at the information that is in it, suppose that I fell in with the elephants or with a star that was collapsing. Well, that star has some information in it. As it's collapsing to form a black hole, that information can't disappear. But we know from just solving Einstein's equations that the surface area of the star becomes smaller and smaller and smaller until it's zero at the very end when it hits the singularity inside a black hole. So it seems clear that the amount of information of the star, whatever it is, at some point is going to become larger than this smaller and smaller and smaller surface area of the star as it gets more and more compressed deep inside the black hole. So then does this mean that this was just some fluke? It's something that applies to particular observers who live far outside a black hole, and there's actually no general relation between information and surface areas? Well, it turns out no. If you state the relation in just the right way, then it's true even deep inside a black hole or in regions of the universe that are very large. And the way you have to state it is actually in a much more physical way. Instead of saying, how much information do I have at this instant of time when my star is really small and has very small surface area? How much information is there still inside the star? You have to ask, well, if I took a picture of that star at this time, just before it got completely crunched into a singular place in space-time, if I took a picture of it, how much of the star would I see? And it turns out that you don't have enough time. The light doesn't have enough time to traverse the whole star before everything gets crunched into the singularity and the game is over. You have to actually calculate this. You have to take my word for it right now. But
I'm taking your word for so much, pal.
But the point is, if you ask, okay, what can actual light rays see? How much information can they see?
Right.
Light rays that come out of the area in question, and it makes absolutely no difference what area you pick, anywhere in the universe, any shape, doesn't even have to be closed. What those light rays see is some piece of the star in this particular example, and by some conspiratorial miracle, it's always less information in that piece of the star than the surface area you started from. It's a much bigger conspiracy of which only the sort of tip of the iceberg was discovered in the context of
Well, it's a little bit like uncertainty in the sense that if you try to measure, you're only going to get a piece of it, but that doesn't affect the existence of all the information. It's all there. The fact that you can't get it or don't have a big enough camera is your own personal psychological problem. It doesn't affect the universe at all.
Well, indeed, if you wanted to ask how much information is there in the universe, then again, it's actually very useful that information is sort of encoded on regions that are seen by light rays. You could just ask, well,
How far?
what is in our past? What is in the region from which light could have reached us up until now? And that region is bounded by basically light rays that are just barely making it to your eyes right now, and they've been traveling for billions of years since the beginning of the universe. And those light rays, well, if you follow them back, of course, they come from a larger and larger region as you follow them back that's farther and farther away. But at some point, their surface area actually becomes very small again when you follow them all the way back to the Big Bang, because everything is small at the Big Bang. The universe is basically contracting to a single point at that point. And so there's a largest area which tells you how much information there is in the universe, somewhere between the Big Bang and us, that is spanned by these light rays. So we can say exactly what the maximum amount of information.
So is it the case on some level that the function of our senses? I mean, you know, Galileo looked at light rays and drew some conclusion about the universe. Are tiny sort of instances of the universe conveying information something that's much bigger, that you're now extrapolating to extreme states of the universe, either in terms of the very beginning of time with the Big Bang or the sort of end of matter in a black hole? That they're part of the same story a little bit?
Well, the interesting thing about the holographic principle, I think all of us probably agree on this, is that it's a statement that can be made in a situation where we understand physics very well. The area that describes how much information there is in the universe that we see is not an area that lives somewhere very close to the Big Bang where we might not trust our equations. The area that tells us how much information there is inside a black hole is not an area that's somehow close to the singularity inside the black hole, which we don't understand as well as we would like to. These are areas in regions of space-time that are arbitrarily well understood. They're completely harmless. They're, you know, Einstein's theory applies.
Harmless is good.
Harmless is always good. I mean, I still wouldn't jump into the black hole, but
right.
They are very, you know, well understood areas. The whole statement takes place in a regime of physics that we completely understand. But what we don't understand ultimately is why it is true. It seems like a conspiracy. Every time you check, it works out. And I think that by itself, I think, was always a huge piece of support for the idea that information isn't lost. All these miracles happen for information not to get lost. It'd be funny if it was at the end. But you have to do it on a case.
Funny.
Your sense of humor is not so
I know, yeah, right. Well, I love apocalypses like the next guy. But Hermann, what is the counter-argument here? I mean, I've got sort of two questions. One is, what is the counter-argument? Who persists with the idea that this holographic principle may be fun to talk about, but in fact doesn't really help us, or there's another explanation?
I wouldn't necessarily say that maybe that people have a counter-argument. But right now, you can state it as a principle because we have indications that it's there. But again, it's basically, still from an intuitive point of view, it's absurd that this would be true. Because again, if we want to describe what's going on, for sure, we're going to tell, okay, well, something is happening here at a given time, or something's happening there. So essentially, the information that you use to describe things, for sure, grows with the volume. And indeed, the equations that we're using to describe physics indeed have all those properties. So right now, we don't have a real way of understanding how this is really true. So we know, we have hints that
there's
it's
no
true.
Evidence?
No, we don't have a mathematical theory that precisely describes how it is. We have strong evidence that it's true. And I think so there were early times, say in the early 90s, where if you would, and I think there was a conference in the early 90s where there was a vote. Okay, how many people were actually believing that information was lost? And then more than half of the hands went up, and there was only a small group of people that were saying, okay, well, we don't believe that information is lost, and it was only a couple of
the rubbish group.
There was the rubbish group, and then there was okay. Well.
Right, and now the rubbish group is bigger. Almost the whole room.
Yeah, if you call us the rubbish group.
Well, you were then. You were then.
Yeah, we were called rubbish. Yeah, that's correct, and proudly so.
How? I want to go back to this information, and I actually want you to go through those slides that I've seen before, which I think are fascinating. But Gerard, let me ask you: is information a particle in the sense that it's like matter? Is information akin to being like electrons, protons, quarks, antimatter? Is it some sort of parallel phenomenon that goes along with reality, or is it something fundamentally different?
No, actually, I think it's about time that we start to disagree with each other. And
no.
So I want to. No, you think so?
Yeah.
Starting to get good.
Because I want to bring in a notion which hasn't been put forward yet. The question of dynamics. You know, when I first saw people windsurfing, I loved also to go windsurfing. So on one day I thought, I'm a theoretical physicist, I can work out how to stand on the board and how to hold the sail without falling over. And I worked it all out, and I stood on the board, I could hand the sail, and I didn't fall over, and I went any direction I want, except I only solved the static problem. I didn't solve the problem, what happens if a big wave comes, and what you have to do if you want to make a sudden turn. This I never solved, so whenever that happens, I fall over. Now here the problem is the same. So far we've been discussing this static question. What is information, where is it, and so on. And you can discuss it at length. But there's something else in physics, the dynamical question. How do things evolve in time, and how do we phrase laws of nature? And now we encounter a deep and fundamental problem, which is the world looks to us three-dimensional. If I make a disturbance here, like I'm saying something or I'm shining a light, the disturbance moves with the speed of light or slower to its environment. And it never goes faster than the speed of light from here to a point far away in the universe. That is a fundamental three-dimensional property of the world as we know. And it has been tested very, very accurately in all branches of physics. It's a very fundamental principle. Not only that disturbances move with a certain maximum speed, it also has causality. That is, whenever you cause some disturbance somewhere, its effect never goes faster than the speed of light, and it certainly doesn't go back in time. Now, this principle we would like to keep. And now holography is standing in our way. It's not doing the thing we want. If my friend Lenny here is right, and information on the two-dimensional surface is completely scrambled, how do you explain it? If you make a disturbance here, the disturbance doesn't spread faster than the speed of light. How would Leah, when she moves her arms in the hologram, how come that the disturbances don't move faster than a given speed in this hologram? There's still something basically wrong with the idea. And that
Why would they have to move faster than the speed of light to work?
That's relativity theory, and relativity theory works extremely well. We don't want to give that up too easily as a fundamental principle. After all, relativity was also a principle that went into Stephen Hawking's derivation. If you throw that away, you're throwing away black holes as well. So life isn't that easy. There's a problem here. So how do we address that? And then I'm coming back to quantum mechanics. We say, well, we used quantum mechanics from the beginning until the end. There's something not quite right about quantum mechanics. And I've been thinking a lot, last decades basically, about there must be something underneath quantum mechanics, some more basic mechanical system that explains why the world that we encounter today looks like quantum mechanical. That could solve this problem, because it could be that in a pre-quantum world, the world is three-dimensional. Information gets lost all the time. In fact, a suspicion I have, and I'm practically the only one in the universe today that has a suspicion that there's an underlying theory in which information gets lost to such an extent that if you have a bulk of material somewhere, so much information gets lost that the only thing that you can retain is what sits on the surface. And that is the reason why, information-wise, you have such a thing as a holographic principle. The only amount of information that you can keep if you have a bucket of water is what sits on the edge of the bucket of water. What happens inside will eventually get lost. Not according to quantum theory, because you just realize, oh, quantum theory preserves information. But there may be a pre-quantum theory in which this information gets lost.
Now,
this
let me just
pre-quantum
say,
theory could be three-dimensional, and then we might possibly find a resolution of this problem.
so is pre-quantum theory something that happened before the Big Bang, or is pre-quantum theory something that happens before you learn
pre-quantum in the logical sense. It
geometry.
is that there is something, that some fundamental principle lying underneath the principle of quantum mechanics.
I see.
Saying we have molecules, we have atoms, we have things smaller than atoms, but smaller than that are things which might not be quantum mechanical. That is my premature explanation as to how to reconcile the idea that the three-dimensional world seems to be two-dimensional by holographic principle, yet there is causality in the three-dimensional sense. This is a problem that has not yet been properly addressed. And I think something should be done about this. If we don't,
Yeah.
we'll never...
So get to work.
Get to it.
If we don't, right. If we don't, we'll never
Forget
get
homelessness,
the good
you guys.
about
Come
what
on.
happens at small distances.
Well, let's put that to Leonard. Is there the possibility of a a more axiomatic kind of
It's not a question
pre-quantum?
of axiomatic.
All right, but then some sort of more basic state than quantum mechanics?
The answer is I don't know. The answer is I don't know. What you're seeing here is an interesting thing. First of all, I would say it should be clear that this whole holographic story is the most radical thing that has happened to our understanding of space, time, matter, since the invention of quantum mechanics and relativity. It is really something very, very different. Where is it going? What is it going to explain? How do we explain it? Well, incidentally, we all agree largely on what we've said up till now. And you'll find that in physics in general, probably in science in general, at any given time there are those things which have been made into established science that people agree on, and that subset they will tend to agree on unless they're screwballs and outside the mainstream of the community. But that once you go past that, once you go even just a little bit past what we really know, you'll start finding it becoming a very, very human subject. A subject with, let's put it this way, good physicists are as variable as snowflakes. Every single one of them is different. Every single one of them has a different perspective. And once you go past that point where we have confirmation, where we do agree, you're going to find that just about everybody has a different view of where it's going to go.
Sure, well, that I can understand. But let's focus on the radicalism for a moment, because I think people can understand how relativity radically changed the Newtonian view of reality, in the sense that the straight lines in the Newtonian world actually are curved in certain spaces, and that curvature relates to the force of gravity in some way. And so around stars, space actually bends. That's a radical notion. It's probably only in the last 30 years that that's been internalized to be something that kind of everybody understands. You can't really appreciate the Matrix, movies like the Matrix, unless you sort of understand the sort of relativistic world. How does this notion produce a radical change in the way that we might see relativity?
I think it's still a work in progress, and we don't know. Harad has his view. I have my view. Herman has his view. What's his name?